Welcome to section 1.8, Proof Methods and Strategy. This is Dr. Gilbert Iyabi, and we are using the text Discrete Mathematics and Its Applications by Kenneth H. Rosen. Section 1.8, Learning Objectives. Number 1, Proof by Cases. Number 2, Existence Proofs. Under existence proofs, we would look at constructive proofs. In this situation, we would be interested in finding values that actually work. And the second would be non-constructive proofs. For non-constructive proofs, we do not actually find particular values that work, but we do prove beyond all reasonable doubt that there exist values that work. And then disprove by counterexamples. We would use that to disprove universal quantifiers for every x, p of x is true. And then non-existence proofs, uniqueness proofs. In other words, we will show that only one unique value would work. The value that works is unique. And then some proof strategies and proving universally quantified assertions. And then we'll discuss the concept of open problems. Now let's begin. Proof by cases. If we have the conditional statement, if P1 is true, or P2 is true, or P3 is true, or Pn is true implies Q is true, we can prove this using the tautology P1 or P2 or Pn implies Q if and only if P1 implies Q and P2 implies Q and Pn implies Q. Each of these are cases. So this is case 1, this is case 2, this is case n. And you see they are all linked up with and, which means for you to conclude that you have proved the conditional statement above, you have to verify that each of these cases hold. Okay? So in other words, all cases must be proved. Proof by cases must be exhaustive. Missing a single case dismantles the entire proof. So proof by cases, usually it's easy, it's straightforward, it's beautiful, but you have to be careful because it has to be exhaustive. For example, if you're proving something for the entire set of integers, which is infinite, then how you divide a set of integers has to be exhaustive. It could be even and odd, that's exhaustive. It could be negative integers, 0, positive integers, that's exhaustive. But if I define it as negative integers and positive integers, guess what? It is not exhaustive. I have missed the point 0. Okay? Of course, if I say something hold for every element in the set S, and the set S has 1, 2, 3, 4, 5 elements, that makes it really easy. I just have to verify that it holds for the first element, and it holds for the second element, and it holds for the third element, and it holds for the fourth element, and it holds for the fifth element, and I'm done. If I verify that it holds for the first 4 elements in the set, and I do not prove or verify that it holds for the 5th element, my proof is not solid. It's not strong enough. Somebody can say, what happens if it doesn't hold for the 5th element? So that dismantles the entire proof. It has to be exhaustive. Proof by cases. Let's look at a few examples. Example 1. Let A and B be defined as the maximum of A and B, which would be A if A is greater than or equal to B, otherwise it would be B. And they want you to prove this associative property. A and B, all of that in parentheses, and C equals A and B and C. So let's go ahead and prove this. I will take you to my own personal screen and reword the problem. So define A and B as the maximum of AB, which is A if A is greater than or equal to B, and it will be B if A is less than B. A and B are real numbers. And the question is, prove the associative property given. Now I have 3 elements, 3 real numbers, A, B, and C. And the maximum of AB would depend on whether A is greater than or equal to B or A is less than B. So I have a couple of cases here. A greater than or equal to B, greater than or equal to C, A greater than or equal to C, greater than or equal to B, and so on and so forth. So there are 6 different possibilities. You have to list every one of them. And these possibilities will have to link A, B, and C. Then we go on and verify each case. We go case by case and make sure that they all work. If that happens, then we can conclude that the associative property given above holds. So let's go ahead and do case 1. So case 1, A greater than or equal to B greater than or equal to C. Now, when you're proving things, at this point, we expect that you would just relax and follow the procedures we have outlined in 1.7. So I want to prove that A and B, all of that in parentheses, and C equals A and parentheses B and C. So I'm going to start with the left-hand side and get a simplified form, then move over to the right-hand side, get a simplified form. And if my simplified forms from the left-hand side and the right-hand side are the same, then I can conclude that I am done. Okay, let's go ahead. So I start off with the left-hand side. A and B and C, parentheses, I deal with my parentheses first. What is A and B? Since A is greater than or equal to B, A and B is the maximum of AB, which is A. So A and B is A, and then of course I maintain my and C, so I have A and C. But what is A and C? A is greater than or equal to B, B is greater than or equal to C. That implies A is greater than or equal to C, therefore A and C is A. So that is my simplified form, and I leave it there. I move over to the right-hand side. A and parentheses B and C, that means I deal with B and C first, and that gives me A and B and C. B is greater than or equal to C, so B and C would be B. So I'm left with A and B. But A is greater than or equal to B, so A and B would be A. So the left-hand side, the simplified form, equals the simplified form on the right-hand side, and therefore I can conclude that the required associative property holds. This proves case 1. Now I have to go through cases 2, 3, 4, 5, and 6 before I conclude. And I would leave all the other cases as simple exercises for serious students. And yes, in class, when you submit your course content or your concept map, I expect you to actually verify all the other 5 cases and then conclude that indeed the associative property holds. That's beautiful. Without loss of generality, WLOG, you would see this very often in proofs. What does it really mean? Well, it's simple. It means that we have a couple of options, which I could loosely use the word cases, but we chose to go with just one option, and that doesn't dismantle our proof. Our proof still holds. That means we have not lost the generality in the proof. Let's take an example to explain that further. Suppose that x and y are integers such that x times y and x plus y are even, then prove that x and y are even. You can go ahead and try direct proof. You'll quickly realize that it's not going to work with direct proof. So let's move on with contraposition. Now, what would be the contrapositive of x times y, x plus y even implies x and y even? The contraposition would be if both x and y are not even, then both x times y and x plus y will not be even. So what does it mean for x and y not to be both even? It means one has to be odd, at least. If one is odd, the other one could either be odd or the other one could either be even, i.e., these are the various options we have. X can be odd. If x is odd, y could be even or y could be odd. If y is even, x can be odd or x can be even. So it doesn't really matter. If we can verify with just one of them being odd, either x or y, we would claim the theorem proved without loss of generality. So in this particular case, without loss of generality, let us assume that x is odd. If x is odd, then there are 2 possible cases: x odd, y even, or x odd, y odd. If we can verify those, then without loss of generality, the problem would be done. If x is odd, then x can be written as 2m plus 1 for some integer m, Now, if x is odd and y is even, what do we have? What would be x plus y? X plus y would be 2m plus 1 plus 2n. Remember, y is even, so y can be written in the form y equals 2n. Again, you can use case like I did before, and if you add all of this up, that gives you 2 into m plus n plus 1. M plus n is an integer, so that is some 2k wiggle plus 1, which is odd, and that works. Remember, what we want to show is that not both x times y and x plus y will be even. So x plus y is odd. Now, let's see, will that hold if y were odd? If y is odd, then y is 2n plus 1. X times y would be 2m plus 1, 2n plus 1, and that gives us an odd number. So we didn't even have to verify all the different cases, but we have definitely concluded that if both x and y are not even, then both x times y and x plus y will not be even. One of them could be even, but at least one will be odd. So we have just a few cases to verify, and we conclude without loss of generality. In class, we would see many more examples that illustrate the concept of without loss of generality, WLOG. We only cover the case where x is odd because the case where y is odd is similar. To use the phrase without loss of generality, WLOG indicates what we have just done. Now let's move on and look at existence proofs. There are two types of existence proofs. The first is known as constructive. For constructive existence proofs, you have to find a value or values that work. For example, show that there is a positive integer that can be written as the sum of cubes of positive integers in two different ways. And you may be asked to provide a constructive proof, or it may just be left open. But in this particular case, it's left open, but we chose to use a constructive proof. And we verify that 1729 can be written as 10 cubed plus 9 cubed. And it can also be written as 12 cubed plus 1 cubed. So what have we done? We have found an integer that can be written as the sum of cubes of positive integers in two different ways, and we're done. We just proved there exists p of x using a constructive proof. What about non-constructive proofs? So for non-constructive existence proofs, as I mentioned before, we prove that there exists a value or values that work without any reasonable doubt, but at the same time, we do not actually point our fingers to any particular value. Example, show that there exist irrational numbers x and y such that x raised to the power y is rational. X is irrational, y is irrational, but x raised to the power y is rational. Well, let's go ahead and prove that without any reasonable doubt. Yet, we're not going to point our finger to any particular value. Now, we do know that the square root of 2 is irrational. We proved this before. So, let's consider the number root 2 raised to the power root 2. If root 2 raised to the power root 2 is a rational number, then root 2 is going to be my x, and root 2 is going to be my y, and I have x raised to the power y being a rational number, and I'm done. I haven't really said my x is root 2 and my y is root 2 definitely. I said if root 2 raised to the power root 2 were rational, then my x will be root 2, my y will be root 2, and I'm done. But if root 2 raised to the power root 2 is not rational, then it will be irrational. So I call it my x. So x will be root 2 raised to the power root 2. And I set my y to be root 2. Then x raised to the power y would be root 2 raised to the root 2, all of that raised to the root 2, and simple properties of exponents. That would be root 2 raised to the power root 2 times root 2. But what is root 2 times root 2? It's just 2. And root 2, all of that squared is 2, which is a rational number. So what have I done? I would have found an irrational number, x, and another irrational number, y, such that x raised to the power y is rational. So either the first case worked, or if it did not, the second case would work. So without actually pointing my finger to some particular x and y, we just proved that there exist irrational numbers x and y such that x raised to the power y is rational. And this is called a non-constructive existence proof. Again, we will see a couple of those in class. Counter examples. If we are asked to prove that for every x, p of x is false, all we need is just one example. All men cry. Well, just find one man that does not cry and we're done. That man is known as a counter example. Every positive integer is the sum of the squares of three integers. Well, go ahead and verify that there is no way you can write 7 as the sum of the squares of three integers. Therefore, the claim is false. And we're done. That is known as a counter example. Now let's move over to uniqueness proofs. Some theorems assert the existence of a unique element with a particular property. And this is the symbol we use for unique. So this statement means there exists a unique x such that p of x is true. There exists a unique x such that p of x is true. Now, if you are asked to prove a uniqueness claim, there are always two parts to this claim. The first part is there exists. The second part is unique. So you have to prove existence. We show that an element x with the property actually does exist. And number two, we have to prove uniqueness. And this is how we would prove uniqueness. We suppose that x and y would work. And then we show that x has to be equal to y. Okay? So suppose x works, y works, prove or show that x equals y. For example, show that if a and b are real numbers where a is different from 0, then there is, okay, that's existence, a unique, that is the uniqueness, real number r such that a r plus b equals 0. So we have two things. We have to prove existence and we have to prove uniqueness. To prove existence, we just solve for r. And that gives us negative b over a. We can divide by a because a is different from 0. So this proves existence. There is a real number, and the real number is negative b divided by a such that a times that real number plus b equals 0. Existence is done. Now what about uniqueness? For uniqueness, we suppose that there exist real numbers r and s such that ar plus b equals 0 and as plus b equals 0. So both r and s satisfy the equation above. But since equal things are equal, both of them equal 0, that means ar plus b equals 0, which equals as plus b, i.e. ar plus b equals as plus b. Now we can add negative b on both sides. Recall that the only thing that can get rid of b would be the additive inverse of b. So if we add b on both sides, b is gone. We're left with ar equals as, and we can use the cancellation property because a is different from 0. If you see an algebra is arguing that a scalar, a real number, is not 0, know that that guy is trying to find the multiplicative inverse of that scalar or to divide by that scalar. So a different from 0, I can use my cancellation property and I have r equals s. So whenever there are real numbers r and s such that ar plus b equals 0 and as plus b equals 0, r would always equal s, i.e. there is a unique number r that satisfies the equation. That proves uniqueness. Existence, uniqueness, and we are done. Now let's talk about proof strategies. When you're proving P implies Q, what are some things you have to do? Number one, try a direct method. If it does not work, then go indirect. Possibly start with contrapositive, and if you find it a little difficult, then try contradiction. Now, for whichever method you are trying, choose a strategy. Do forward reasoning, which is what we've done with almost all the problems, or you could use backward reasoning. Now, let me show you an example that illustrates backward reasoning. Suppose that two people play a game taking turns, removing 1, 2, or 3 stones at a time from a pile that begins with 15 stones. The person who removes the last stone wins the game. Show that the first player can win the game no matter what the second player does. That is pretty hard to imagine a direct proof. So what you do is you think backward. Let n be the last step of the game. Player 1 can win if the pile contains 1, 2, or 3 stones because you can remove 1, 2, or 3 stones. But if that were to happen, player 2 will have to leave such a pile if the pile that he or she is faced with has 4 stones. But for that to happen, player 1 can leave 4 stones when there are 5, 6, or 7 stones left at the beginning of his or her turn. But for that to happen, player 2 must leave such a pile if there are 8 stones. And then backward, player 1 has to have a pile with 9, 10, or 11 stones to ensure that there are 8 left. And for that to happen, player 2 needs to be faced with 12 stones to be forced to leave 9, 10, or 11. But for that to happen, player 1 can leave 12 stones by removing 3 stones. Now we look at the proof. If you were to do the write-up, you say the first player can ensure a win by removing 3 stones and leaving 12. And then you go downwards right up to the solution. That is called backward reasoning. Universally quantified assertions. If you are asked to prove the assertion for every xp of x, you say let C be a random number from your domain. If you can prove that P of C is true, then by the universal generalization of our universal quantifier, for every xp of x would be true. So for example, an integer x is even if and only if x squared is even. So we say let x be an arbitrary number from the domain. Suppose x squared is even. We verify that x is even. Okay. Now we already showed this in section 1.7. So I'll let you go back and verify the proof. If x is an arbitrary number that is even, then its square is even. You do that using direct proof, and then the reverse, you do that using contraposition or contrapositive. Now, there are other proof methods and strategies we have out there. For example, can we tile the standard checkerboard using dominoes? So right here, that is the standard checkerboard, and these are dominoes. Can we use dominoes to tile the standard checkerboard? Well, we can actually do it and say done. You don't have to write anything. We just take our dominoes and we put them in order, put them in order, put them in order. We line them up and we say, this is one possible solution. All we need is just one solution. And we have a solution, so that is done. We can make it even more exciting. Can we tile a checkerboard obtained by removing one of the 4 corner squares of a standard checkerboard? So our checkerboard has 64 minus 1 equals 63 squares. Each domino has 2 squares. A board with a tiling must have an even number of squares. Since each domino has 2 squares, a board with a tiling must have an even number of squares. Therefore, 63 is not even. We have a contradiction. That's not going to work. And even more exciting, example 3. Can we tile a board obtained by removing both the upper left and the lower right squares of a standard checkerboard? So we get this square out, we get this square out. Can we tile this using dominoes? There are 62 squares in the board. To tile it, we need 31 dominoes. Each domino covers 1 black and 1 white square. Therefore, the tiling covers 31 black squares and 31 white squares. Our board has either 31 black squares and 32 squares, or 32 black squares and 30 white squares, so that cannot be done. Okay, just regular reasoning. I like the whole dominoes, checkerboards. You may find a couple of them at the end of the chapter in your textbook, and we may look at a few more in class. Now, before we conclude, let's talk about open problems. The role of open problems. Open problems are very important. They are called unsolved problems, and they have motivated much work in mathematics. One famous open problem was known as the Fermat's last theorem. I actually met a medical doctor who was really interested, and he told me he found somewhere that Fermat's last theorem was open for a long time, and he and I have fun just talking about Fermat's last theorem. What makes Fermat's last theorem really important? Well, it simply says the equation x to the n plus y to the n equals z to the n has no solution in integers, where x times y times z is different from 0, as long as n is greater than 2. You're like, what does that even mean? Well, you would actually come to appreciate this if you recall that the Pythagorean theorem states that x squared plus y squared equals z squared. Remember, the square of the hypotenuse equals the sum of the squares of the two other sides of a right-angled triangle. That is Pythagorean theorem. If A, B, and C would work in a Pythagorean theorem, we call ABC a Pythagorean triple. So the question is, now that I know that x squared plus y squared can equal z squared for some right angle triangle, what about x cubed plus y cubed equals z cubed? X to the power 4 plus y to the power 4 equals z to the power 4. X to the power 10 plus y to the power 10 equals z to the power 10. Well, Fermat played with this and gave us an open problem that lasted for over 300 years. And it simply says Pythagorean theorem is where we end. After Pythagorean theorem, n greater than 2, x to the power n plus y to the power n equals z to the power n has no solution in integers. It could have solutions in real numbers, but no solution in integers. And mathematicians played with that until very recently, 1990, when Andrew Wiles found a proof for it. So check around for open problems and try your hand on it. Who knows? You might be the next person to solve an open problem. For example, the 4-color conjecture was around for a long time. You could color any map of the world using at most 4 colors. It was around for a long time, and finally it was proved that it's an open problem, or those were open problems. And before we conclude, let's talk about additional proof methods. Later, we will see a couple of other proof methods. Mathematical induction. Prove that a property holds for every natural number n. We would see that in this class. We would see it in abstract algebra. We will see it again in advanced calculus, in abstract algebra 2 and in advanced calculus 2. It's a very important proof method in mathematics. And then we'll look at structural induction, Cantor diagonalization, and some combinatorial proofs like the one I just mentioned, the 4-color theorem. Thank you very much for going through chapter 1 with me. We are now going to go on to chapter 2, and we will start looking at set theory. What are sets? When are sets equal? How do we bring in the concept of proofs into sets? We'll see all of that in chapter 2. Thank you, and God bless you. Bye-bye.